Hi class, so this is the continuation of our discussion about determinants. Okay, so let's consider the matrix. Okay, so this is a matrix A. Okay, and these are the corresponding elements of this matrix A. Okay, so here, okay, if we are going to be asked, okay, to solve for the determinant of this matrix A. So as we can see, this is a 4 by 4 matrix. So this is a matrix of order 4. Okay, so we have already discussed how to solve for the determinants of order 2 or 2 by 2 matrices and determinants of order 3 or 3 by 3 matrices. Now, what if the given matrix is already a matrix of order 4 or 4 by 4 matrix? Okay, so what if the matrix is already 5 by 5, 6 by 6, and so on? Now, what if our matrix, okay, is has an order, okay, higher than 3? Okay, can we use basket method for that? Okay, so class, the answer is no. Okay, we cannot use, okay, basket method in solving 4 by 4, 5 by 5, 6 by 6 matrix. Okay, so that basket method is just for 3 by 3 matrices. Okay, so here for 4 by 4 matrices, 5 by 5 matrices, 6 by 6 matrices, and so on. Okay, we are going to use, okay, we are going to use the methods that I am going to discuss. Okay, so let's start our discussion for this. So the first method that we're going to discuss is called cofactor expansion method, or it is also called Laplace expansion method. So for this method, it allows to reduce the computation of an n by n determinant to that of n minus 1 by n minus 1 determinant. So let's say you have a 4 by 4 matrix, or you have a 4 by 4 matrix, and you are asked to solve for its determinant. So we cannot use basket method to solve for the determinant of 4 by 4 matrix. Okay, so what we're going to do if we use this method is that 4 by 4 matrix, okay, it will be reduced to 3 by 3 matrix. Okay, if you use this method, no? So that's how it works. Okay, it reduces an n by n matrix into n minus 1 by n minus 1 matrix. So meaning to say, if from 4 by 4 matrix, it is reduced to 3 by 3 matrix, if it's already 3 by 3 matrix, you can now solve the determinant of that 3 by 3 matrix using basket method. So it's also the same. If example, the given matrix is 5 by 5. So if it's 5 by 5, if you use this method, this cofactor expansion method or Laplace expansion method, that 5 by 5 matrix will be reduced to 4 by 4 matrix. But since 4 by 4 matrix, we cannot still solve for its determinant using basket method. So we have to use again this method, okay, so that it can be reduced to 3 by 3 matrix. And if it's already 3 by 3 matrix, we can now use basket method to solve for its determinant. Okay, so if that's the case, we use this method twice, okay, in order to reduce that 5 by 5 matrix to 3 by 3 matrix. Okay, so that's how we use, no, this method in solving for n by n matrix wherein the order is higher than 3. Okay, so our step for this method is, the first one is you have to choose a row or column of the matrix A. Okay, so it is suggested that you choose a row or column that has many zeros. Okay, so after you chose the row or column from the matrix that you're going to use, okay, for this method, okay, you can now proceed to the second method, which will be this formula. So the formula to determine the determinant of matrix A will just be equal to the summation of negative 1 raised to m plus n times A times mn times minor of a m n. So as you can see here, this negative 1 raised to m plus n, okay, times minor of a m n, as you can notice, this is actually a cofactor, right? This is for a formula for cofactor of a m n, right? So that's why it's called cofactor expansion, no? This method is called cofactor expansion because we are going to use the cofactor. Okay, so what we're going to do is multiply, okay, the cofactor of that element, okay, of the element a m n to the element itself, which is AMN. Okay, so we are just going to to solve for that, no, for all the elements, okay, that from all the elements from the row or column that we chose. Okay, we just have to sum the product of of each element, okay, and the cofactor of that element. Okay, so let's start solving using this method. Okay, so let's solve this sample problem. So find the determinant of matrix A using cofactor expansion method or Laplace expansion method. Expand about the first row, and then letter B, expand about the second column. So as you can see here, our given here is a 3 by 3 matrix. So the cofactor expansion method or Laplace expansion method, it can also be applied, no? It can also be used in solving 3 by 3 matrix. But the thing is, it will not be so much useful, okay, in solving for the determinant of matrix A, because we know that we have basket method, and it's much easier, okay, actually, no. But I will just show you here, okay, that we can actually use this method in solving for 3 by 3 matrix. Okay, so we are asked here to in letter A to expand about the first row, no? So meaning to say this will be our chosen row. Okay, for letter A, so we are asked here for uh, to solve this 3 by 3 matrix using cofactor expansion method, okay, using the first row. So we will expand this matrix, no, about the first row. So this will be our first row. Okay, and we are going to use this formula, okay, in solving for the determinant of this 3 by 3 matrix. So again, this is a summation of the cofactor, no, cofactor of uh, each element, no, in the chosen row times the element itself. Okay, so let's start solving this. Okay, so the determinant of matrix A will just be equal to for your from the chosen row, so we will use this row. This is the first row, no? So from your first row, so the first element here is 2. So we are going to solve for um, the cofactor of 2. So the cofactor of this element 2 is determinant of, so we're going to delete the first row and first column here. So the determinant of 4, 2, 5, 3. So that will be the minor, no, times the sign convention. So for this element, this is located in this position. So the sign convention here is positive. So this will be positive here. So that will be the cofactor. And we are going to multiply also that cofactor by AMN. So by the element itself. So that will be times 2 here. Okay, so this will now be the cofactor times AMN of element 2. Okay, so we will also do the same to the next element, which is 3. Okay, so for element 3, the cofactor of this element 3, we just have to delete the first row and second column. Okay, and then we solve for the determinant of the remaining elements, which are 1, 2, negative 1, and 3. So these are that element 1, 2, 1, 2, negative 1, and 3. So we just solve for its determinant. That will be the minor times the sign convention for 3. So the sign convention for 3 is positive, negative. So that will be the sign convention. It will be negative. That's why it will be multiplied by negative here. Okay, and then it will be multiplied the by the element itself, which is 3. Okay, so that will be for element 3. Now for element 0, okay, so since that same element, no, that element itself, which is 0, it will be multiplied to its cofactor. So it will be useless to solve for its minor, because if it's multiplied by 0, it will just be 0. Okay, that's why it is said in the steps for solving using this method, it is said that it is advisable that you choose rows or columns with many zeros. Okay, so this is the reason, because if the element is 0, automatically you don't need to solve anymore for the minor, no. So it will be useful, no, that that concept will be, or suggestion, no, it will be useful. Okay, so here we are going to solve for the determinant of this and this. Okay, so solving for this. Okay, so the determinant of this is 2 times 2, positive 2, no? And then this will be minus here since that is negative. This is negative. Okay, so that this will be minus. And the determinant of this is 5 times 3. So this will now be the determinant of A. So solving for this is 2 minus, or 4 rather, 4 minus 15. So this will be negative 11. So this will now be the answer, okay, for the determinant of matrix A. So this is actually the same answer, okay, that we had using basket method. So we already solved this matrix A from our previous examples using basket method, no? So this is the same answer. So of course, it has to give you the same answer, okay, though it's a different method, no? So we just showed here that we can really apply cofactor expansion method or Laplace expansion method in 3 by 3 matrices, no? Ayun. So we are also asked here to solve this, no, by expanding about the second column. So our chosen column here is second column. So let's solve for letter B. Okay, so we will use the second column, no, for our formula to solve this using cofactor expansion method. So our second column will be this column. Okay, so applying the formula here, so the determinant of A will just be, so for the first element, that is 3. Okay, and you just have to solve for the cofactor of this element 3. So delete the row, delete the column, and then solve for the determinant of the remaining elements, 1, negative 1, 2, and 3. Okay, and we just multiply the sign convention for this element. So the sign convention here is negative, since positive, negative. Oh, so this will be negative. That's why it's negative here. Now, proceeding to the next element, which is 4. Okay, so it will be 4 times the cofactor of that element, no? So we just have to delete the row and column, okay, wherein that element is located, and then find the determinant of the remaining elements. So that will be 2, 0, negative 1, 3. We just have to solve for its determinant times its sign convention. So the sign convention for this element is positive, negative, so it will be positive here. That's why it's positive here. Now for the last element, that is 5, so that will be 5, and then solve for its cofactor. We just have to delete the row and the column and solve for the determinant of the remaining elements, 2, 0, 1, 2. Okay, that will be 2, 0, 1, 2. So multiplied by the sign convention of 5, which is this will be positive, negative, positive. So it should be negative here. So this will be negative here. So solving for this, the determinant of A, that this will just be negative 3 times 5 plus 4 times 6 minus 5 times 4. Okay, if we input that, so actually you don't have to input that in your calculator. You can solve that manually. Okay, but it is actually equal to negative 11. So this is the same answer, okay, using the first solution, which is expanding the matrix about first row, no? So um, even if you choose another row, okay, so whether any row, okay, any row you chose, okay, as your as the row or column that to use to expand the matrix, okay, it will be, or it will give the same answer. Okay, so this will now be the answer, no? So the determinant of A is negative 11. Okay, so let's start solving now a 4 by 4 matrix using cofactor expansion method or Laplace expansion method. So this is our given matrix, no? So again, this is a 4 by 4 matrix, so we cannot use basket method, okay, in solving for its determinant. Okay, so for our solution here, since in the problem, okay, it is not given, okay, the row or the column, okay, that we should use, no, for cofactor expansion method or for Laplace expansion method, no? So it's not given. Okay, so we have the freedom, okay, to choose, okay, what row or column we are going to use, okay, for our solution. Okay, so here again, it is easier, okay, if you choose a row or column that has many zeros. Okay, so in this case, as you can see here, this second row, okay, this second row actually has 2 zeros, right? So if we choose this, okay, it will be it will be okay if we choose this row, okay, since there are two zeros here. And also, as you can see here, if you choose third column, okay, there are also two zeros in the third column, okay, so you can also choose that, no? So it depends to you, no, what row or column you're going to choose. But it will be advisable if you choose either row 2 or third column, since they are the rows or columns that have many zeros. Okay, so in this case, okay, so we are going to use, okay, second row. So we will expand this matrix, okay, using the second row. Okay, so we will use that. So we will use this formula again. So it will just be the summation of the element times its cofactor. Okay, so in this case, we chose the second row. So applying the formula, so this will be the determinant of matrix A. So the first element here is 1. No, so this will be 1 and it will be multiplied by its cofactor. So the cofactor of 1, okay, will be we have to delete the column and the row and find the determinant of the remaining elements: 3, 4, 1, 5, 0, 3, 2, 1, 6. So this will be that matrix. We have to solve for its determinant times the sign convention. So for the for this element, okay, its sign convention is, so we will start from positive and then negative. So your element here, it should be negatives. That's why it is negative here. Okay, and then proceeding to the next element, that is 4. So we just have to rewrite 4 and then multiply it by its cofactor. So the cofactor of 4, we have to delete the column and the row and then find the determinant of the remaining elements: 2, 4, 1, and then negative 1, 0, 3, and then 3, 1, 6. Okay, so this will be that matrix. Okay, times the sign convention for 4. So the sign convention for this, if 1 is negative, if this element is negative, so it should be positive here. That's why it is positive here. And also, proceeding to the next element, that is 0. So no need to solve for this element, since if it is multiplied by its cofactor, okay, so it will just also be 0. And same for this last element. So it will just be 0. So from here, it will be a shorter solution since we chose the row or column that has many zeros, so it will be easier, no? Ayan. So from here, okay, so we can now solve the determinant of this 3 by 3 matrix using basket method. Same with this 3 by 3 matrix. So solving for the determinants of this 3 by 3 matrices, okay, so we can see that the determinant of this first matrix is actually negative 100. Okay, and the determinant of this second matrix is 53 if we use basket method. Okay, so you can use basket method to confirm if if these are the right answer for determinants, no? So we are going to simplify this. So the determinant of A will just be negative 100, negative 1 times negative 100, that will be positive 100, plus 4 times 53. Okay, so that will be 312. So this will now be the determinant of matrix A, no? That will be 312. So we will now proceed to our next method, which is Chios method or pivotal condensation method. So the purpose of this method is also the same as the purpose of our of the first method that we have discussed. Okay, so this method also allows to reduce the computation of an n by n determinant to that of n minus 1 by n minus 1 determinant. So if we have a let's say 4 by 4 matrix here, so it's the same with uh, cofactor expansion method, no, that from 4 by 4 matrix, if we use Chios method, it will be reduced into 3 by 3 matrix. Okay, and then from that, we can use basket method to solve for that determinant. Okay, so if it's 5 by 5, so again, if you use Chios method, it will be 4 by 4. And then you have to use Chios method again, okay, to make it 3 by 3. Okay, and from that, you can use basket method to solve, no, for the determinant of that given matrix. Okay, so these are the steps, okay, for solving determinants okay, of n by n matrix, okay, using Chios method. Okay, so the first step is choose any element AMN except 0 as pivot. Okay, so our second step, we can determine determinant A, okay, by using this formula, 1 over AMN raised to n minus 2. Okay, so times the reduced matrix. So in our example, we will talk about that reduced matrix. Okay, so we're in A, Mn, that is our chosen element. So that is any element, okay, as long as that element is not 0. Okay, so you cannot choose a 0 element, okay, from your matrix as your pivot. Okay, so and then, because if you choose 0, okay, if you put that here in our formula, okay, this fraction will be undefined, right? So, we cannot choose 0 as your AMN or as your chosen element as pivot. Okay, so, and then your n here, okay, is the order of matrix. Okay, so that is the number of row of your matrix, no? That's the order. Okay, so that's our step now. So we will talk about the reduced matrix mentioned here, okay, in our examples. Okay, so let's solve this sample problem. So find the determinant of matrix A using Chios method or pivotal condensation method. So to solve this, our first step is to choose an element. Okay, so we have to choose an element other than 0. Okay, so we can choose any element here. Okay, so in this case, we are going to use A11, okay, as our pivot. No? So this will be our chosen element. A11. So this will be 2, no? Okay, so from that, we are going to apply our formula. So our formula for determining the determinant of A, it will just be 1 over AMN, or the chosen element, raised to n minus 2, wherein n is the order or number of rows. No? So in this case, the number of rows here is 4. So our n here for our formula, it will be 2, 4 rather. Okay, so applying our formula, again, that will be 1 over our chosen element, which is 2. A11 is our chosen element. And then, raised to n, our n is 4 minus 2. Okay. Times, okay, now, we are going now to solve for the reduced matrix. So, our reduced matrix, okay, so that's why it is called reduced matrix, because from our given, that is 4 by 4 matrix, okay, it will be 3 by 3 matrix here. Now, for the elements, okay, for the reduced matrix, okay, so let's say for this first element, so it can be obtained, okay, from the pattern, okay, that we are going to follow here. Okay, so since A11 will be our pivot, so this element, it will be included in all of the 2 by 2 matrices here, as you can see here. Okay, so this element will be included in all of this 2 by 2 matrix. So we have to form this 2 by 2 matrices. Okay, so because the elements of this reduced matrix, okay, will come from this 2 by 2 matrices. So if we solve for the determinant of these 2 by 2 matrices, okay, so if we solve for their determinant, that will be the element, okay, that will be the resulting element, okay, of our reduced matrix. Now, how did we obtain these 2 by 2 matrices? No? So, from our given, okay, so again, we are going to use this element, A11, as our pivot. So, we are going to follow this pattern, okay, that for our first element, it will just be 2, 1, 3, 4. Okay, so that is the first square matrix form, no, using this pivot. So again, that will be 2, 1, 3, 4. So that will be our first element. The next element will be 2, 1, 4, 0. So that will be that 2 by 2 matrix form. Again, 2, 1, 4, 0. So since from here, we are going to move to the right, no? So we are just going to move to the right as well. But the pivot here will remain. Okay, so that will be again 2, 1, 4, 0. Okay, so that will be that 2 by 2 matrix for this second element. Now for this third element, we are just going to move to the right, okay, from here. Okay, so using our pivot, so that will be 2, 1, 1, 0. Okay, so that will be the 2 by 2 matrix here. Okay, now for the second row, okay, so we are going to go down. Okay, so using again our pivot, so our pivot is 2, so that will be 2, negative 1, and then 3 and 5. 2, negative 1, 3, and 5. So that is our pattern. Okay, so 2, negative 1, 3, and 5. Okay, so since we are going to move here to the right, okay, so we are also going to move here to the right. So that will be 2, negative 1, 4, 0. So that is the 2 matrix, that will 2 by 2 matrix that will be formed here. 2, negative 1, 4, 0 for this matrix, no? Now for the third element here, or for the third 2 by 2 matrix here, okay, so we will just move to the right again. So that will be 2, negative 1, 1, 3. Okay, so that will be for our third 2 by 2 matrix here. Now for the third row, so again we are just going down. So since we go down here, okay, so we're just going down here as well. So that will be, so using our pivot again, so that will be 2, 3, 3, 2. So that will be 2, 3, 3, 2. Now for this 2 by 2 matrix, we're going to move to the right. So that will be 2, 3, 4, 1. So that will be 2, 3, 4, 1. Okay, so for our last 2 by 2 matrix here, we are going to move to the right again. That will be 2, 3, 1, 6. Okay, that will be 2, 3, 1, 6. So we are just going to follow that pattern, okay, to form these 2 by 2 matrices here. Now, after we have formed this 2 by 2 matrices, okay, we are going to solve for the determinant each of these 2 by 2 matrices. Okay, so the answers for this will be for this 2 by 2 matrix. Its determinant, okay, it will just be 2 times 4 minus 1 times 3. So that will be 5. And here, 2 times 0 minus 1 times 4. So that will be negative 4. And here, 2 times 0 minus 1 times 1. So that will be negative 1. And here, 2 times 5 minus negative 1 times 3. So that will be 13. And here, 2 times 0 minus negative 1 times 4. So that will be positive 4. And then here, 2 times 3 minus negative 1 times 1. So that will be 7. And here, 2 times 2, that will be 4. Minus 3 times 3, minus 3 times 3, so that will be negative 5. And then we have here 2 times 1 minus 3 times 4, so that will be negative 10. And then we have here 2 times 6 minus 3 times 1, so that will be 9. Okay, so this will now be our reduced matrix now. Okay, so from this reduced matrix, okay, so also don't forget the fraction here. Okay, okay, so simplifying this, so this will be 1 over 2 raised to 4 minus 2, so that will just be 1 over 2 squared, no? So that will be 1/4. Okay, so this will now serve as a scalar quantity, right? So now we are going to solve for the determinant of this 2 by 2 matrix. So solving for the determinant of this 2 by 2 matrix, or 3 by 3 rather, using basket method. Okay, so the answer for that will be 1,248. Okay, times 1/4. Okay, so 1,248 times 1/4. So that will be 312. So this will now be the determinant of this matrix A. Okay, so again, we use Chios method here. Okay, so from this 4 by 4 matrix, okay, it was reduced, okay, to this 3 by 3 matrix. And since this is already a 3 by 3 matrix, we can apply basket method here to solve for its determinant. And after we solve for its determinant, we just multiply here. Okay, so this will now be the answer, okay, for the determinant of this matrix A. So this is 312. Okay, so let's solve sample problem number 2. So find the determinant of matrix A using Chios method or pivotal condensation method. So as you can see here, our matrix A here is a 5 by 5 matrix. So again, we cannot use basket method here. Okay, we cannot use basket method directly to solve for its determinant. Okay, so we are going to use Chios method, okay, or pivotal condensation method. And using this method, this 5 by 5 matrix will be reduced to 4 by 4 matrix. But if it's still 4 by 4 matrix, so we cannot use basket method directly, no? So we have to reduce that again. Okay, we have to use Chios method again to reduce that 4 by 4 matrix into 3 by 3 matrix. And from that 3 by 3 matrix, okay, we can now use basket method. So in short, for 5 by 5 matrices, we are going to use Chios method twice. Okay, we're going to use Chios method twice to reduce this 5 by 5 matrix to 3 by 3 matrix. Again, this will be our formula, okay, for solving the determinant of this matrix A using Chios or pivotal condensation method. Okay, so again, we have, for our first step, we have to choose an element. Okay, so that element should not be 0. Okay, so it can be any element. Okay, and then raised to n minus 2. So our n here again is the row, number of row, or the order, no, or the number of row of the given matrix. So in this case, our n here is 5. Okay, since this is 5 rows, right? Okay, this has 5 rows, no? Okay, so now let's start solving this by choosing first, okay, our element here, okay, that we will use as our pivot. Okay, so in this case, we are going to use A34. So that will be the element located at the third row and fourth column. So again, you can use any element, no, as long as it is not 0. So in this case, we are going to use this element. So this is 3. Okay, so this will be our AMN, and then our N, again, that will be 5, no, since the number of rows from our given matrix is 5. Okay, so we are now going to substitute that in our formula. Okay, so that will be 1 over 3 raised to 5 minus 2. Okay, now for our reduced matrix, so again, our reduced matrix, it will be formed, okay, by determining, okay, the determinants of this 2 by 2 matrices form, okay, by following, no, the pattern, okay, that I've mentioned from the previous example. So in this case, our pivot is 3, okay, this element. So again, this element, it will be included, okay, in all of these 2 by 2 matrices here, okay, in our reduced matrix. Okay, so for our first 2 by 2 matrix here, it can be formed, okay. So again, we will use our pivot. So that will be formed by this element. So that will be 2, negative 1, and then 1, 3. Okay, so again, that will be 2, negative 1, 1, 3. Now for our second element, or second 2 by 2 matrix here, so we are going to move to the right. Okay, so that will be 3, 5, 1, 3. Okay, so our pivot here will not move. Okay, since that is our pivot. Okay, so again, that will be 3, 5, 1, 3. Again, that will be 3, 5, 1, 3. Now, for this next 2 by 2 matrix, so we will just move to the right again. So that will be 4, 2, 1, 3. So that will be 4, 2, 1, 3. Now, for the element or the 2 by 2 matrix here, okay, our last 2 by 2 matrix here. So we are going to move to the right again. But here, our pivot, okay, will be put, okay, in the first row. Okay, since our pivot is here, okay, and the elements that we need here is 8, 4, no? So this will now become 1, 3, 8, 4. Okay, so that will now be the arrangement of this 2 by 2 matrix here. So that will be 1, 3, 8, 4. Again, that will be 1, 3, 8, 4. Okay, now for the second row, okay, so we will again follow that pattern. Okay, so that will be 1, negative 1, 0, 3. Okay, so we will use 3 as pivot. Okay, remember that. So again, that will be 1, negative 1, 0, 3. So this will be that 2 by 2 matrix, 1, negative 1, 0, 3. Now for the second 2 by 2 matrix here. So we will just move to the right. That will be 1503. So that will be 1503. Okay, so for the next 2 by 2 matrix, that will just be 0203. So that will be 0203. Now for our last 2 by 2 matrix here in the second row, that will just be 0324. So that will be 0324. Okay, so now for the third row, okay, so we will just move downward here. Okay, so what will happen here now, it will now become, so again, our pivot here is 3. Okay, so this will now become negative 1, 3, 3, 6. Okay, negative 1, 3, 3, 6. Okay, so we will move to the right for this 2 by 2 matrix. So that will be 5, 2, 3, 6, 5, 2, 3, 6. Okay, so for the third 2 by 2 matrix here, we will move to the right again. So this will be 2, 1, 3, 6. 2, 1, 3, 6. Okay, so again, for the last 2 by 2 matrix here, we will just move to the right. That will be 3, 6, 4, 2. So this will become 3, 6, 4, 2. Now for our last row here, so we will just go down here. So 3 is still our pivot. So this will become negative 1, 8, 3, 4. Negative 1, 8, 3, 4. Okay, for this next 2 by 2 matrix, it will be 5, negative 9, 3, 4. So that will be 5, negative 9, 3, 4. So for our next 2 by 2 matrix here, we will just move to the right. So that will be 2, 7, 3, 4. So that will be 2, 7, 3, 4 here. Okay, so moving to the right again. So this will be 3, 4, 4, 1. 3, 4, 4, 1. Okay, so from here, we just have to solve for the determinant of all these 2 by 2 matrices. Okay, so let's solve this. Okay, so for this fraction, so this will just be 1 over 3 cubed. So that will be 1 over 27. Okay, so solving for the determinants of these 2 by 2 matrices. Okay, so for this first 2 by 2 matrix, it will just be 2 times 3 minus negative 1 times 1. So that will be 7. So for this next 2 by 2 matrix, it will just be 3 times 3 minus 5 times 1. So that will be 4. And then we have here 4 times 3 minus 2 times 1. So that will be 10. And then we have here 1 times 4 minus 3 times 8. So that will be negative 20. And then 1 times 3 minus negative 1 times 0. So that will be 3. And then we have here 1 times 3 minus 5 times 0. So that will be 3. And then we have here 0 times 3 minus 0, minus 2 times 0, so that will be 0. And then we have here 0 times 4 minus 3 times 2, so that will be negative 6. And then we have here negative 1 times 6 minus 3 times 3, so that will be negative 15. And we have here 5 times 6 minus 2 times 3, so that will be 24. And then we have here 2 times 6 minus 1 times 3, so that will be 9. And then we have here 3 times 2 minus 6 times 4, so that will be negative 18. And then negative 1 times 4 minus 8 times 3, that will be negative 28. And then 5 times 4 minus negative 9 times 3, so that will be 47. And then 2 times 4 minus 7 times 3, so that will be negative 13. And we have here 3 times 1 minus 4 times 4, so that will be negative 13 here. So as you can see here, so again, this is a 4 by 4 matrix. So we are going to use Chios method again, okay, to reduce this to 3 by 3 matrix. So from here, okay, so we will choose an element again, okay, that we will use as our pivot. So in this case, let's choose A12. So we're going to use the element in the first row and then second column. So this will be that element, no? So we will use this element, okay, to solve this again. Okay, so let's proceed to the next slide. Okay, so this will now be the continuation. Okay, so again, from 5 by 5 matrix, from the given 5 by 5 matrix, it was already reduced into 4 by 4 matrix. And from that 4 by 4 matrix, we have to reduce that again, okay, to 3 by 3 matrix. So again, we will use 4 as our pivot. Okay, so we will apply again, okay, our formula for Chios method. So this 1 over 27 here, it will just be included here. So don't forget to include that, because if you forget to include that, your answer will be wrong. Okay, so here we will apply here our formula. That will be 1 over uh, AMN, which is 4, raised to n minus 2, wherein our n here is 4. So this is a 4 by 4 matrix already. Okay, so we will just multiply this, no, this constants. Okay, so from our formula. Okay, again. So again, we will multiply that to our reduced matrix. Okay, so our reduced matrix here. Okay, so we will again follow our pattern here. Okay, to obtain this 2 by 2 matrices here. Okay, so again, 4 will be our pivot, so it will be included in all of the 2 by 2 matrices here in our reduced matrix. Okay, so for the first 2 by 2 matrix, it will be formed from this pattern. So this will be 7, 3, 4, 3. Okay, 7, 3, 4, 3. And then for this 2 by 2 matrix, we will just move to the right. So this will remain here. So this will be our pivot. Okay, so this will be 4, 3, 10, 0. That will be 4, 3, 10, 0. And then for our last matrix here, so we will just move to the right. This will be 4, 3, negative 20, negative 6. So this will be that 2 by 2 matrix. So for our next row, okay, we will just move downward. So this will become 7, negative 15, 4, 24. 7, negative 15, 4, 24. We will just move to the right. So this will now be 4, 24, 10, 9. 4, 24, 10, 9. Okay, so we will just move to the right again. That will be 4, 24, negative 20, negative 18. So this will be that 2 by 2 matrix. Okay, so for our third row here, we will just move downward again. So this will become 7, negative 28, 4, 47. So that will be 7, negative 28, 4, 47. And then we will just move to the right. So this will be 7, negative 28, 10, negative, no. So this is our pivot. So our pivot is this, no? So for our next 2 by 2 matrix here, it will be 4, 47, 10, negative 13. Okay, so for this last 2 by 2 matrix, we'll just move to the right. So that will be 4, 47, and then negative 20, negative 13. Okay, so from here, after forming this 2 by 2 matrices, we will solve for the determinant, okay, for each of these 2 by 2 matrices. Okay, so we will simplify first this, the fraction here. Okay, so this will be 1 over 4 squared, no? So that will be 1 over 16. So it will just be 1 over 27 times 1 over 16. And then solving for the determinant of these 2 by 2 matrices. So this will be 7 times 3 minus 3 times 4. So that will be 9. And then for the next 2 by 2 matrix, that will just be 4 times 0 minus 10 times 3, or 3 minus 3 pala, minus 3 times 10. So that will be negative 30. And then we have here 4 times negative 6 minus 3 times negative 20. So that would be 36. Then we have here 7 times 24 minus negative 15 times 4. So that will be 228. And we have here 4 times 9 minus 24 times 10. So that will be negative 204. And then we have here 4 times negative 18 minus 24 times negative 20. So that will be 408. And then we have here 7 times 47 minus negative 28 times 4. So that will be 441. And then we have here 4 times negative 13 minus 47 times 10. So that will be negative 522. And then we have here 4 times negative 13 minus 47 times negative 20. So that will be 888. So from here, okay, so we are going to simplify this. So 1 over 27 times 1 over 16. So that will be, where's my calculator? Okay, so again, that will be 1 over 27 times 1 over 16. So that is 1 over 432. Now, we are going also to solve for the determinant of this 3 by 3 matrix. So since this is already a 3 by 3 matrix, we can use basket method, okay, to solve for its determinant. So solving for the determinant of this 3 by 3 matrix, it will be negative 83,376. Okay, so it will be multiplied by 1 over 432. So that is the product of these two fractions. Okay, so dividing that or multiplying this 1 over 42 times negative 83,376. So it will give you negative 193. So this will now be the determinant of this matrix A. Okay, so also for as an important note, okay, so the value of determinant, okay, it's always a whole number. So there is no determinant that is a decimal number, okay, or a fraction. So the value of the determinant, okay, it's always a whole number. Okay, since all the elements here, okay, in our matrix are all whole numbers. Okay, so our determinant should be whole number. Okay, so this will now be our determinant. But our determinant, it can be negative. As you can see in this problem, no, our determinant here is negative. Okay, so this will now be the answer for this sample problem. Now, let's proceed to the adjoint of a matrix. So the adjoint of a matrix, it is the transposed cofactor of the matrix. So we have already discussed about cofactor, right? Cofactor of elements. Okay, so we are going to solve for the cofactor of the matrix, okay, by solving the cofactor of all the elements. Okay, so the elements of the cofactor of the matrix, okay, will be the cofactor of each of the element, okay, in our matrix. Okay, so after we solve for the cofactor of a matrix, okay, to solve for its adjoint, we just have to transpose it. Okay, so we have already discussed that also. Okay, that to transpose a matrix, we just have to interchange rows and columns. Okay, so let's try to solve problems, okay, about this. Okay. So let's solve this problem. Find the adjoint of the matrix A. So our matrix A here is a 3 by 3 matrix. So we are going to solve its adjoint. Again, our adjoint is the transpose cofactor of the matrix. So we have to solve first for the cofactor of this matrix. So to solve for the cofactor of this matrix, we just have to solve for the cofactor of all the elements, okay, of this matrix A, no? So for our solution, okay, so for the cofactor of matrix A, okay, so for the first element, which is 1, we just have to solve for its cofactor. So its cofactor is we just have to delete the corresponding row and column and solve for its determinant. So this 2 by 2 matrix, this will be that 2 by 2 matrix. So that will be 3, -1, 2, -2. Okay, and its determinant, okay, if we solve for its determinant times its sign convention, that will be the cofactor. Okay, so our sign convention here is positive. Okay, so this will just be positive. Okay, so if we solve for the determinant of this 2 by 2 matrix, it will be the cofactor, okay, of this first element. No, now for this second element, we just have to solve for its cofactor. Okay, so to solve for its cofactor, again, we just have to delete the corresponding rows and columns. Okay, and solve for the determinant of the remaining elements, or that will be formed, no, from the remaining elements. So that will be 4, 6, 2, -2. So this will be that matrix, no, and we just have to solve for its determinant and multiply it to its sign convention. So the sign convention for the element located here is negative, so it will be negative here. So this will now be the cofactor, okay, of this second element. No, now for our third element, we just have to delete our row, the corresponding row and column here, and solve for the determinant of this. So this will be 4, 6, 3, and -1. So this will be that matrix. No, so we just have to solve for its determinant and multiply it to its sign convention, which is positive. So this will now be the cofactor of that element. Now for the next element here, okay, so we are just going to solve for its cofactor by deleting the corresponding rows and columns and solving for the determinant of the matrix form from the remaining elements. So that will be 5, -3, -1, -2. Okay, and multiply this no to the sign convention, which is negative. So that will now be the cofactor of that element. Now for this element, so it will just be to solve for its cofactor, we just have to delete the corresponding row and column and solve for the determinant of the matrix form from the remaining elements. That will be 1, -3, 6, -2. Okay, so that will be the same, okay, for the remaining elements here, element 2, element 6, element -1, -2. So we just have to solve for their cofactors, and that will be their cofactors, okay? So that will be the elements, okay, of the cofactor of matrix A. Okay, so after we solve for the determinant of these 2 by 2 matrices here, which are the cofactor, okay, of these elements, okay, so it will give you this matrix. Okay, so this will be -4, 20, -22, 13, 16, 31, 19, -14, and then -17. So this will now be the cofactor of matrix A of the given matrix A. So from here, to solve for its adjoint, we just have to transpose this cofactor. So we just have to interchange the rows and columns. So that will now be our adjoint. So we just have to interchange rows. So these rows will become column here, -4, 20, -22. This second row here, 13, 16, -31, will become the second column here, 13, 16, 31. And then the third row here, 19, -14, -16, it will become the third column here, 19, -14, -16. So this will now be the adjoint of matrix A. Okay. Now let's proceed to the inverse of a matrix. So if we have matrix A, its inverse is denoted by A raised to -1. Okay, so there are two ways or methods to determine, okay, the inverse of a matrix. So the first one is by using this formula. So this is inverse of matrix A. That will just be equal to the adjoint of A over the determinant of matrix A. Okay, so the adjoint of A, we have already discussed that from our previous slide, no? So, or previous, previous slide. Okay, so that will be our first method. For our second method, it will be A, or your matrix A multiplied by your inverse matrix, which is your unknown. It is equal to identity matrix I. So for our identity matrix I, so again, the principal diagonal, okay, for that matrix I, okay, they are all 1. Okay, so that's our definition for identity matrix or unit matrix, right, in the types of matrix that we have discussed. So again, all the principal diagonal, okay, for that matrix I is 1, and all the remaining elements are 0. Okay, so we can use that this formula, no, for to solve for our inverse matrix. So we will discuss this in our example, how to use that this two methods. Okay, so let's go to our sample problem. So find the inverse of the matrix A given here. So we will solve this the inverse of this matrix using the two solutions. So we're going to use first our solution 1, okay, using this formula. So A raised to -1, or the inverse of matrix A, that will just be equal to the adjoint of A over the determinant of A. Okay, so this is actually the example that we answered, okay, from our discussion about or our example about adjoint of a matrix. So this is that same matrix, no? So from that example, no, so we already have the adjoint of A. Okay, so again, this is the adjoint of A that we have solved from the example that we had in the topic adjoint of matrix, no? So this is already the adjoint of A. Okay, so we also need the determinant of A. So solving for the determinant of matrix A, okay, so using basket method, it will give you 162. Okay, so don't get confused here, class, ha? So the determinant, okay, that we need here is the determinant of A. Okay, don't get confused, okay? So it's not the determinant of adjoint of A that we need, okay? So again, the determinant that we need here is the determinant of the given matrix A, not the determinant of the adjoint of A. Okay, so our determinant of matrix A here again is 162 if we use basket method to solve for this 3 by 3 matrix. So from that, we just substitute that in our formula. So the adjoint of A is this, and the determinant of A is 162. So from here, we are just going to apply scalar division here. Okay, so applying scalar division, each element will just be divided by 162. So this will now become our inverse, okay, for matrix A. So this will be inverse of matrix A is equal to negative 4 over 162 is negative 2 over 81. And then 13 over 162, so it cannot be reduced further. No, so for our next element here, that will be 19 over 162. Okay, and then 20 over 162, so that will be 10 over 81. And then 16 over 162, so that will be 8 over 81. And then negative 14 over 162, so that will be what is that? Negative 14 over 162. So that will be negative 7 over 81 now. And then we have here negative 22 over 162. So that will be negative 11 over 81. And then 31 over 162. So we cannot reduce that further. And then negative 17 over 162. So it cannot be reduced also. No, so that would be negative 17 over 162. So this will now be the inverse of matrix A. So this will now be the answer using solution 1. So now using solution 2, so again, this is A times the inverse of A is equal to I. Okay, so this will be our formula now. Okay, so this is our matrix A. And then for our inverse matrix, we will assign unknown variables here or unknown quantities here, okay, that will represent, okay, the elements, okay, for our inverse matrix of A. So we will assign here A, B, C, D, E, F, G, H, I as the elements, okay, the unknown elements, okay, those. So these are the quantities, okay, that we are going to solve, okay, for this, no, to solve for the inverse matrix of inverse rather of matrix A. So we will equate this to identity matrix, no. So since this is 3 by 3 matrix, so of course our identity matrix will also be 3 by 3. So for our identity matrix, all the elements in our principal diagonal here, okay, are 1, okay, and the remaining elements, okay, are 0. So this is the identity matrix that we need here. Okay, so we are going to perform here, okay, the operation here. Okay, so this is actually multiplication. Okay, and then we are going to equate this. So we are going to apply equality of matrices here. No? So let's first multiply A and this matrix 3 by 3 matrix. No? So we are going to multiply them. So multiplying them, so it will be 1 times A plus 5 times B plus negative 3 times G, right? So that's our rule for multiplying matrices, right? So for our next element here, so that will be the first row, and then the second column, you multiply them. So that will be 1 times B plus 5 times E plus negative 3 times H. So this will be that element, no? Okay, for the next element here, so we will just multiply the first row and the third column. So that will be 1 times C, 5 times F, tapos plus negative 3 times I. So this will be that element. Now for our next element here in the second row, so this will be multiplication of the second row and first column here. Okay, so that will be 4 times A plus 3 times D plus 2 times G. So this will be that element. And then for the next element, so that would be 4 times B plus 3 times E plus 2 times H. Okay, so this will be that element. For the last element here, it will just be 4 times C plus 3 times F plus 2 times I. Okay, so for the last row, so this will just be the multiplication of the third row, okay, and the first column. So this will be 6 times A plus negative 1 times D. That's why it's negative here. And then plus negative 2 times G. So this will be that element. And then we have here 6 times B plus negative 1 times E plus negative 2 times H. So this will be that element. And then we have here 6 times C plus negative 1 times F plus negative 2 times I. So this will now be that element. So we will equate this, okay, to our identity matrix here. Okay, so again, we are going to apply equality of matrices here. Okay, that this element, so it will just be equal to the corresponding element to the right side of the equation. So this will be A plus 5D minus 3G. It will be equal to 1. Okay. So again, it's been duplicated here. So again, A plus 5D minus 3G, that will be equal to 1. Okay, so for the next element, 5 plus B plus 5E minus 3H equals 0. And then we have here C plus 5F minus 3I is equal to 0 also. And then we have here 4A plus 3D plus 2G, that will be equal to 0. Then we have here 4B plus 3E plus 2H, that will be equal to 1. And then 4C plus 3F plus 2I, that will be equal to 0. And then we have here 6A minus D minus 2G, that will be equal to 0. And then 6B minus E minus 2H, that will be equal to 0. And then we have here 6C minus F minus 2I, that will be equal to 1. So this will be that equality, no? So from here, as you can see here, for this first column, okay, we have here 3 equations and we have here 3 unknowns. The unknowns here are A, D, and G, but we have 3 equations. So we can solve for these 3 unknowns using these 3 equations. Okay, so just to solve this, okay, we can use elimination. We can also use substitution, no? So we can also use calculator techniques, okay, to solve this easily, no? So we can use mode 5-2. So mode 5-2, we just have to input, okay, the coefficient, okay, of the variables here, okay, and the constant in the right side, no? So let's input this. So for our first equation, that will be A plus 5D minus 3G is equal to 1. So if we input that in our in mode 5-2, no, in the table in mode 5-2, so that will be 1, 5, negative 3, and then 1. So for the next equation, so that will be 4, 3, 2, and then 0. So for the next equation, that will be 6, negative 1, and then negative 2, and then 0. So if you solve for that using your calculator, so the values for the value for A is negative 2 over 81. The value for D is 10 over 81, and then the value of G will be negative 11 over 81. So that will be the same way, okay, that you're going to do, no, to solve for the unknowns 5EH here in the second column. Okay, so to solve this, again, mode 5-2, we can use mode 5-2. Okay, so we just input the coefficients here and the constants at the right side. So this will be for the first equation here. So 5 plus B plus 5 is minus 3 is equal to 0. So that will be 1, 5, negative 3, and then 0. So for the next equation, that will be 4, 3, 2, and then 1, and then 6, negative 1, negative 2, 0. Okay, so the answer here is 13 over 162. For B. For E, that will be 8 over 81. For H, that will be 31 over 162. So also for the third column here, so these are also 3 equations and 3 unknowns. So mode 5-2 again. So that will be, for the first equation, that will be 1, 5, negative 3, and then 0. And then we have here 4, 3, 2, 0. And then we have here 6, -1, -2, then 1. So for the value of C, that will be 19 over 162. For the value of F, that will be -7 over 81. For the value of I, that will be -17 over 162. So this will now be the elements, okay, of the inverse of matrix A, okay, that we are solving. So if we arrange this, okay, so this will now be the inverse of the given matrix A. So this will now be the answer. So that concludes this discussion. So I hope that you learn and I hope that you attain the learning outcomes for this topic. And reminder that there is a CM assessment task for this topic. So don't forget to answer that and submit that on our next meeting. Okay, so God bless class, keep safe, and bye-bye.